likes dust except for people who study dust. And I don't study dust. So, so this is how to get rid of the dust, okay, hopefully. So to do that, we want to talk about dust attenuation curves, okay? So you take a galaxy, remove all of its dust, and then you get its true intrinsic SED, okay? But this is the one that you actually observe, which is affected by the dust, especially at shorter wavelengths. So the dust attenuation curve is when you divide this observed SED, or the intrinsic SED with the observed SED. Typically express it as magnitudes, so magnitudes of attenuation at different wavelengths. Now, we want to actually normalize that so that we don't really talk about if one galaxy is dustier than the other. That's okay. We care about the shape of this attenuation curve, okay? So how does it change with wavelength with respect to some reference wavelength, which we typically take to be V, at V band, okay? But it doesn't really matter where you do that. Now, getting these curves is very challenging because specifically we don't really know necessarily what is this intrinsic SED. So what is that we want to learn about the curves? Well, first of all, we'd like to know at the current redshift, what is a typical curve, okay, like the average of the galaxies. We also want to know if there is some variations among one galaxy to another, okay, how much variation there is, this diversity. And does this diversity correspond to, does it relate with any of the global parameters like the mass of the galaxy or something else? And then specifically for the typical curve, today you want to compare it to typical curves at previous epochs, okay? So why do you want to do that? As I said, even if you don't really care about dust, we care about removing its effects, okay? So what do? Oftentimes in the SED fitting is we actually assume an attenuation curve, okay? So that's what our models tells us, okay, this is how much light you should see based on this assumption. A lot of packages that we use for SED fitting actually do that. Then the question is what to assume, okay? And as I'm sure you're familiar, the popular choices are like the Calzetti curve, which is a relatively shallow curve, which means that for a given amount of AV attenuation, it doesn't have that much more UV attenuation. Like the opposite example would be SMC curve, where for the same amount of AV attenuation, you have much more far UV attenuation, okay? And there's also Milky Way curve, which has this interesting UV bump feature of extra attenuation at 2200 microns. I should mention that both SMC and Milky Way curve are actually extinction curves, not attenuation curves. So we do not know how our galaxy would look from the outside, really, in terms of its attenuation coming from all the different stars in the galaxy and the dust that's in it. Why is that important? Because if one assumes one curve, for example, Calzetti curve, and compare that to what you would calculate for specific star formation rates, if you assume some other curve, they can be big systematics, okay? And sometimes we don't really take that into account. So what can we do to try to constrain these curves and hopefully on a galaxy by galaxy basis? Well, I'm going to use the SED fitting. Now, I just said that typically we assume a curve in the SED fitting, but it's not actually necessary to assume the curve. One could allow the curve to be a free parameter. And specifically, for simplicity, we parameterize the curve with two numbers. One is the slope, and the second number is the intensity of the UV bump. And slope, in particular, a parameterization that is now quite popular is to take the Calzetti curve, which would have a slope difference of 0. So 0 means it is a Calzetti curve, no bump, okay? And then change the slope by a power law addition to it, which minus means it's steeper than the Calzetti curve, okay? So how do we do this with the SED fitting? Well, it is quite problematic unless you have the infrared constraints, okay? It is possible to do it, but a lot of degeneracies between the amount of dust, age of the populations, and the curve. All these three, it's a three-way degeneracy, basically. But if you would have infrared luminosity, you could use that as a constraint on the energy that has been absorbed by the dust. So it's the classical energy balance game that we can play. Now, we're talking here about low redshift, SDSS galaxies, infrared. Information comes from WISE. It's at short wavelength. Okay, does not capture the entire infrared. So, but we would like to have this total infrared luminosity to be able to do this constraining. Okay, so we do one trick. Okay, instead of trying to actually do the SED fitting of the infrared SED, which has a lot of, there's no information for the far infrared, we actually use infrared-dependent templates and just the 22 micron point to figure out what the infrared luminosity is on its own, without any SED fitting, just based on the luminosity-dependent templates. And then we use this infrared luminosity as a constraint in the SED fitting. Okay, so it's the SED fitting that has photometry points plus the infrared luminosity as sort of like a point that we fit. So I call this the SED plus LIR fitting. And we show that we can actually get very accurate infrared luminosities that match very well with the Herschel, even with this one point. So now we do the SED plus LIR fitting for the sample. That is something like 250,000 galaxies from SDSS. We also use Galax for the ultraviolet. And this is part of a bigger catalog that has something like 700,000 galaxies, so including the ones for which we do not have infrared information, that you can, it's publicly available, Galax SDSS, WISE Legacy catalog, has star formation rates, stellar masses, other things that you want to know at low redshift. So what happens when we do this exercise? Now, each galaxy can be constrained in terms of the attenuation law. Its slope and the bump strength even, though not very accurately, still there is useful information. So how do we present this information here is we look at the SSFR stellar mass diagram and we show the average slopes, okay? So on the left-hand plot, it is all of the galaxies, and here is only like the main sequence galaxies. What you see here is there is actually some trends, okay? Not all galaxies have the same slopes. Actually, the range is staggering, okay? So this light region is actually close to the Calzetti curve in terms of the slope. And as you go to lower masses, it gets steeper and steeper. SMC is around here, it gets even steeper than the SMC curve. So it's a huge diversity in slopes. Now, this may look like there is some mass dependence here, okay? Actually, it turns out this is a second order effect. The primary effect is between the slope and the amount of dust in the galaxy. Now, so don't get confused. We have the curve is just the shape. Okay, you can have a little bit of dust or more dust, but here there seems to be a correlation between if you have not much dust, the curve is actually very steep. And there's a lot of dust, it is flatter, it is more gray. There's not much difference in terms of how much you attenuate UV versus the optical. So you can see that here, this is AV, this is the mass, and you see all these lines are sort of horizontal. So it's a very strong dependence on the AV. So where does the dependence on the mass come? Because more massive galaxies are dustier. So they would tend to have shallower curves. So here I directly show slope versus AV, and you can see this. And what is interesting, that's what the radiative transfer models actually tell us is happening. It has to do with the mix of scattering that is very wavelength dependent and absorption, which is not. And if there's a lot of dust, absorption takes over the scattering. So we believe that is the explanation for that. So again, the same plot that I showed, if we take just one slice in AV, you can see that the mass dependence has gone away. But there actually is some dependence on the SSFR as well. So, and right now we don't really know whether the radiative transfer models quite explain that. So that will be something to look into that. Another thing that comes to mind is inclination of the galaxy, right? How the curves may be changing with the inclination. So here you can see, again, the mass. These are edge-on, face-on. And you can see that these lines are not vertical. So that there is some dependency, especially for big galaxies which actually have disks. These galaxies don't have disks. For them, it doesn't really matter. But again, if you take just a small slice in AV, this goes away. So it's the total amount of dust. Doesn't really matter whether your galaxy is inclined or it's just face-on has a lot of dust. If there is so much AV of dust, the attenuation curve is pretty much the same. What about the bump? Well, here, the trend also exists such that massive galaxies seem to have a little bit of bump. So a Milky Way, if we could see its attenuation curve, would probably have much less bump than its extinction curve based on this. Whereas low mass galaxies actually have to have higher, stronger bumps. So this actually looks opposite from the trend Milky Way versus SMC, which again is just the extinction curves. And recent work from Desik and Narayanan and also some previous works have shown that that's really the case. So these are the geometric effects, okay? That when the curves are shallow, which also means a lot of dust, the bump goes away. So if you look at just the average curve, there's a lot of range for individual ones, but look at the average one. It's actually kind of as steep as the SMC curve. For practical purposes, if you want to do SED fitting, it's actually good to split your sample by stellar mass and then apply different curves. And it is also interesting that for galaxies around 10 to the 10, there was a work a few years back by Charlie that was getting these points here, which I agree almost perfectly with what we find in this method that we actually look at individual galaxies. In practical sense, it is still okay to use a single curve, okay, and neglect the variations. But you'll be just adding some SFR error, okay? But one should be using the appropriate curve. So you basically add something like 0.15 dex of error in the star formation rates, okay? Now, what about moving to higher redshifts? In CANDELS, I started looking into applying the same methodology, and there we have 24 micron point to do that. First test was to see whether the 24 micron SFR, just naive conversion from the luminosity, agrees with the SED fitting star formation rate without infrared constraint before we combine that. It seems okay, actually. There's also 100 microns, but it's not really used. So when you do derive the curve in the same way, so the light blue is local, and this one now is Z of 1. Seems to be slightly below that. But one should keep in mind that infrared detections from 24 micron do not actually get, a lot of galaxies are not detected, okay? So what do? Well, we say, well, let's maybe not even use infrared because we don't have it. And let's first check how bad that is, not having the 24 micron constraint. Well, this is the comparison of slopes with and without it. And there's a correlation. The slopes get really poorly determined, but there's no systematic difference. So if you're only interested in like the average curve and not individual galaxies, so that we had to give up. And we do all of the galaxies, Z of 1. This line lies exactly on top of Z of 0. Going further to the redshift of 2, well, here things get messy because it seems like 24 micron has this axis, and other people have seen that as well. So we don't know why they do not agree with just the UV-corrected SED star formation rates. Maybe AGN, maybe something else. So we don't use that at all, okay? So again, we just do it without the infrared luminosity, and we get this curve now that is slightly higher than the Z0 and the Z01, which is the same. And actually, that sort of agrees with what Brett and Casey were doing, that they are finding that most of the galaxies Z02 have this delta less than 0. But this sample was actually infrared selected, so there are some differences there, but I think that at least qualitatively it does agree. By the way, there is a clear correlation between RX beta diagram and the attenuation curve slopes, as like Richard was showing the other day. Why I'm showing this? because we would like to see some independent confirmation of that result that the curves are very steep at 0, 2. And that one possible result that leads in that direction is this. So these are the purple points are the stacking infrared access points from Reddy et al. Recent analysis that uses stacking of MIPS and PACs. So they actually do use that information. And this is the local redshift 0 median curve. So the RX beta seem to agree very well. The RH beta points seem to agree very well, from which then, by the token of this correspondence being there, we say that that also should mean that the curves are also very similar. So we seem to see a lot of evidence that the curve is actually not evolving much. Presumably, there's a lot of scatter at each redshift, but as I said, that scatter does not seem to really introduce so much problems when you do the star formation rates. But picking a curve that it may not be appropriate may do that. Okay, so to summarize, locally, we can actually determine these curves on a galaxy by galaxy basis. We find a huge diversity, both in slopes and in intensities of UV bump. It seems that this diversity mostly comes from just the amount of dust in the galaxy. So like the dust column density there. And that agrees with most of the radiative transfer models, although details still need to be worked out, because all of the models assume some extinction curve, which then they pass through the geometry to get the end result. We don't know how much of a diversity there is in the extinction curves. We know that SMC and Milky Way are very different, but we don't have that much information. We have some information from the GRBs and so on. But it does go in the right direction. And from the practical standpoint, this does help us understand how we can deal with the effects of the dust. So like the main takeaway that curves seem to be very steep, like SMC steepness. There may be a little bit of bump there, but again, not something that should be worrisome for calculations of star formation rates. Like when you do NUV color, NUV minus FUV color, that should not be affected really much by the bump because it's a small bump. And I also showed preliminary results on Redshift 1 and 2 using exactly the same analysis, except that we had to give up using the infrared constraints, especially 0.2, where we don't really understand where the 24 micron is coming from. And it seems to show that there isn't much evolution in the curve. And I should say that that's the reason why there may not be much evolution in the curve, even though the galaxies are dustier and you expect the curves to be shallower. It's because there's the opposite effect, is that the galaxies with very high SSFRs tend to have steeper curves. So the two effects seem to cancel. That's what the preliminary are finding. I wasn't showing that. That actually conspires to make the end curve be remarkably constant with time. Thank you.
Super. Time for questions. Okay. Well, no microphone. Go for it, Susan.
Have you thought about, or have you used the Charlotte and Fall or the Ardenal attenuation extinction curve? Sorry, attenuation curve?
So Charlotte and Fall, they have a model in which you actually have different attenuation for young and old stars. It is already there. Okay. What is different is they assume that this curve that is being then modified by star population is a curve with a power law of minus 0.7. And we find that to be very shallow, that is not sufficient. You have to let that be free. And that if you would do that, then it will agree with that. Have not tried, but I believe that would bring it closer probably to these results. Yes.
All right, next question, Charlie.
So you mentioned the trend with the slope with star formation rate.
Yes.
And it's probably hard to imagine how that would play into the radiative transfer models. But could that be the signature of the changing extinction curve? You might imagine that the different radiation field would lead to different grain populations.
That would actually be similar to what we believe may be going on with the SMC. right, where the strong radiation fields may change the size distribution of that. So that may be more of a dust grains effect than the geometry effect. And that I think it would be possible to test that. Okay, yes, but that's a great suggestion. Yeah.
Other questions?
Okay.
Do you have data, or have you tried this on individual regions in star-forming galaxies, distinct galaxies?
So yeah, like a result, yes. Not yet. My collaborator Mederic is working on that. We have to think hard about what it means to have attenuation curve on the result patches of the galaxy. But it will still be interesting to try to break down things and see what may be going on and whether we see the same kind of trends that we see on global scales.
I just want to clarify, you were saying that the trend is really with the overall attenuation
Yes.
of the curves, not necessarily the star formation rates, just that they all correlate.
Yes.
That's what we found with infrared SAM papers and what Blake said.
That's right.
You said using the average attenuation law,
Mm-hmm.
is that taking that into account, that it's correlated with the overall attenuation?
No, it's just the full sample, and you just average it over the full sample without anything. But we do have like binned in different specific. Yes.
Time for another question?
Have you made any tests on the inclined galaxies, depending on the size of the galaxy?
So size is not something that we have looked at, but
Could you repeat the question?
I'm sorry. So the question is whether we have also looked at both the inclination and the size as independent parameters. And I have not looked at the size. That's something that has been suggested to me. That there may be some effects there. I think what Aryan has shown may actually, there are some differences in different, depending on declination and size as well. So yeah, you should look into that. Thank you.
Thank you very much, Samir. Let's thank our speaker again.